What are Hamiltonians in adiabatic quantum computing? Have you ever wondered how quantum computers solve complex problems? One key player in this fascinating world is the Hamiltonian. In the context of adiabatic quantum computing, Hamiltonians are mathematical tools that representing the total energy of a quantum system at any moment. They are essential for guiding the computation process. Let's break it down. The journey begins with an initial Hamiltonian, often referred to as H sub I. This Hamiltonian has a ground state, which is the lowest energy state of the system. This state is relatively easy to prepare, making it a great starting point. The goal is to transition to a final Hamiltonian, labeled H sub F, which is more complex and encodes the solution to a specific computational problem in its lowest energy state. The magic happens when we slowly change the Hamiltonian from H sub I to H sub F over time. This is done using a time-dependent Hamiltonian, represented as H of t equals S of t times H sub I plus 1 minus S of t times H sub F here. S of t is a smooth function that shifts from 1 to 0 during the computation. According to the quantum adiabatic theorem, if this change is gradual enough, the system will stay in the lowest energy state throughout the process. At the end, measuring the final state reveals the solution to the original problem. Hamiltonians create energy landscapes. The initial Hamiltonian represents a simple landscape with a known minimum, while the final Hamiltonian represents a more complex landscape where the minimum corresponds to the solution. The quantum system effectively rolls down this landscape to find the global minimum energy state that holds the answer. In practical applications, Hamiltonians in adiabatic quantum computing are designed to tackle optimization problems, simulate quantum chemistry, and address various computational tasks. For instance, many difficult problems can be framed as finding the ground state of a Hamiltonian that represents a cost function. Companies like D-Wave utilize quantum annealing, a form of adiabatic quantum computing, to solve optimization challenges by physically realizing these Hamiltonians and evolving the system accordingly. The efficiency of this computation hinges on the spectral gap, which is the energy difference between the ground state and the first excited state of the Hamiltonian during the evolution. A larger spectral gap allows for quicker evolution without leaving the ground state, whereas a smaller gap necessitates a slower evolution to maintain the adiabatic process. In essence, Hamiltonians in adiabatic quantum computing are the evolving energy operators that guide the quantum system from a simple starting point to a final state that encodes the solution to a computational problem. This approach focuses on energy minimization and preparing the ground state, showcasing a unique method in the realm of quantum technologies.